Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the lecture 2 of module 6. In the module 6, we have been discussing about seismic waves in a spherical earth, and we are also going to talk about body wave travel time studies. In the lecture today, we are going to cover the following concept. First, we will have a recap of what we have learned in the previous lecture. Then we will discuss about the velocity distribution in the spherical earth. Especially we will be seeing how the rays are passing through the different kind of material of having different kind of velocities, such as the low velocity zone and the high velocity zone and the normal earth situation where the velocities are smoothly varying. Then we will be learning about the concepts of triplication and shadow zone. Then we will see the travel time curve inversion, and then we will see the summary of today's lecture. In the recap, in the previous lecture, we have learned that to study the crust and upper mantle, the flat layer assumption is more convenient, whereas to study the deep earth structure, spherical earth is more concise. The ray parameter for the spherical earth is given by following expression, that is P is equal to R sin I by V. Rays leaving the source at different angles have different ray parameters, and different rays with different P bottom at different depth. Which means that we have seen that if suppose there is a source at the surface and there is a receiver on the surface, then the rays that are leaving from the source will be going down, and since the velocities are increasing with depth, the rays will bend away from the normal, and at a certain point they will bottom and then start to go upward and then recorded at the receiver. The source can generate several rays, so that all the rays will be having the different ray parameter. So those different ray parameters will be bottoming at different depths. Ray path and travel time for flat layer and spherical earth can be visualized as P is equal to 1 by Cx, where Cx is the horizontal apparent velocity, that is equal to 1 by d delta by dt, and that can further be equal to dt by d delta, that is basically the slope of the travel time curve in case of the flat layer earth. Similarly, for the spherical earth also, the ray parameter can be taken as the slope of the travel time curve for the spherical earth, and that is equal to r sin I by v. Ray path, travel time and the angular distance for the spherical earth can be expressed as Tp is equal to integral of ds by v, that is equal to integral from the lowest point of the ray, that is the bottoming depth, that is Rp, to the point of the epicentral depth, that is R naught, zeta square dr divided by R in bracket zeta square minus P square to the power 1 by 2. Similarly, for the angular distance as a function of ray parameter is equal to integral over the infinitesimal d theta, that is equal to 2p integral over bottoming depth to the epicentral depth dr by r in bracket zeta square minus p square to the power 1 by 2. As far as the today's lecture is concerned, we are going to consider three cases. Case 1, where the offset distance is increasing as the ray parameter decreasing. Then we will consider second case in which we will see how the triplication occurs in case of a high velocity zone. And then there will be the third case where we will see how the shadow zone occur in case of low velocity layer in sandwiched in between the high velocity layers. So the first case is, we know the velocity generally increases slowly with depth in case of the normal earth situation. So what will happen in that case? If the source is generating the rays over here, then the rays, since they are experiencing the velocity increment as they go deeper down the earth, then finally they will bottom and then start going upward and then will be recorded at the receiver. So if you look at these rays, what you will observe, the ray parameter is going to decreasing if you go away from the source. That means with distance, the ray parameter is decreasing over the surface, and that is what it is written. Rays that bottoms deeper at a location with small rp and greater vp ultimately emerges further from the source because it has a smaller p. So if you will see here, the rays that are having a small takeoff angle will be having the smaller ray parameter, and the rays which are having the larger takeoff angles will be having the larger value of the ray parameter, because we know that P is equal to R sin I by V. So V's R and V are basically constant for each of the rays. The only thing is different is the takeoff angle. That takeoff angle, if it is increasing, the ray parameter will increase. If the takeoff angle is decreasing, then the ray parameter will be decreasing. So if you go in this direction, then what you will see, the ray parameter is decreasing. But as you are decreasing the ray parameter, the lower ray parameter ray will be recorded at a larger distance. So what is written here? Thus the ray parameter decreases and travel time increases monotonically with distance. The travel time curve T delta will be concave downward because its slope P delta decreases with distance. So if you look at this particular figure here, this is the T X plot, or you can say the travel time and the angular distance plot. Since we know that as you are going away from the source, then the ray parameter is decreasing. So the slope of the travel time curve gives the value of the ray parameter. That is why the slope should keep on decreasing. So this should have a concave downward slope, or you can say the shape of the travel time curve should be concave downward. And in that case, dp by d delta should be less than 0, because with distance the p is decreasing, and that will be equal to d square t by d delta square. Now if you look these things on the intercept slowness curve, then intercept slowness curve will be somewhat like this, and it will be smooth. And on the ray parameter distance, since the ray parameter is decreasing with distance, then it should be somewhat like this. Now generally in earth, the offset distance with respect to ray parameter will increase as p decreases. That is what we learned. That is, as the takeoff angle decreases, the range increases. In this case, where dx by dp or d delta by dp will be less than 0, we say that this branch of travel time curve is prograde. So this basically known as prograde motion, because the p is decreasing with increasing x. So we can say this is a prograde motion, and this is the velocity model of the normal earth situation, where the velocities are smoothly increasing with depth. And what you have seen is that the if you go from here to there, then you will encounter the rays consisting of lower ray parameter and hence traveling the larger distance on the surface. Now the second case is of triplication, which occurs in the case of high velocity zone. So if you look at this model of velocity, then you will see the velocities first are smoothly increasing, then suddenly there is an abrupt increase in the velocities, and then it start again to increase smoothly with depth. So this particular area this area here, where the velocities are abruptly increasing is known as the high velocity zone. So in this case, what happens as you decrease x, then p also decreases. So you know in the normal earth where the velocities are smoothly increasing, as you increase x, p decreases. But in this case, as you decrease x, the p decreases. So what happens in this range, in this particular zone, what happens is that whatever rays will be coming in this zone, then it will be bottoming up and then recorded at a shorter distance. So what you will see in that case, dx by dp will be greater than 0 and it shows retrograde motion. And when you will in this case also, the p as you go in this direction will be decreasing, but x will also be decreasing. But in the previous case, when the velocities are smoothly increasing, then x was basically not decreasing, it was increasing as p was decreasing. So this is what it is written in the normal case. When the p was decreasing, x was increasing. But in case of high velocity zone, p is decreasing, but x is also decreasing. And this shows the retrograde motion, and this shows the prograde motion. Now let's understand this in a more detailed manner. So this is your velocity profile or velocity model, and velocities are smoothly increasing, and then there is a sudden increase in the velocity and the velocities are again smoothly increasing. And this is your source, and you can see that the rays which are in the zone of the velocities above the high velocity zone, then those are basically going and then being recorded at the stations on the surface. And if you go from A to B, then there will be a decrease in the ray parameter. And then when you are going from C to D, then there is again decrease in the ray parameter. But once you go from B to C for the red rays, then that is coming from the high velocity zone. So they will be having the retrograde motion, and hence there in this case dp by d delta will be greater than 0. So between A to B, dp by d delta is less than 0. Between C to D, the dp by d delta will be less than 0. But between B to C, the dp by d delta will be greater than 0. So in terms of the travel time curve, or if we plot this situation on tx plot or tx plane, then what you will observe, there will be two forward branches, this one and this one. But there will also be a branch that will backward in nature, that will be showing the retrograde motion, and the forward branches will be showing the prograde motion. The end of the backward branch, or you can say the end points of the backward branch BC, will be showing the caustic. That means at those 2 points B and C, the value of dp by d delta is going to be infinity, because at those points the ray will be concentrated and will be showing the very large amplitude. In theory, those points should have the infinity amplitude, but in reality those points just have the larger amplitude. So between B and C, what you will see in this particular zone here between B and C, if you go up, then you will see three kind of waves. One is related to the forward branch, another one is also related to the forward branch, and the next one is related to the backward branch. Since you are observing three kind of waves at the same distance from the source, then this phenomena is known as triplication. I again repeat, between C and B there are multiple rays, three rays, hence this is called triplication. This can also be represented as on the P and X plane, because sometimes the things are not clear on the TX plane, so we plot PX plane. then on the px plane, if we see this thing, then what you will observe is that then if you go from here, if you go at this particular offset distance, then if you go upward, then you will experience three rays coming at this particular distance. And this phenomena, as we have explained, is related to the triplication. The branch that is depicted by black color is the prograde motion. Between B to C is the retrograde motion, and between C to D is the prograde motion again. So at point B and C, dp by dx will be infinity, or dx by dp will be equal to 0. The point B and C are the end point of the triplication, are termed as caustics. Energy will be focused at these points, since rays at different takeoff angles arrive at same range and would theoretically have infinite amplitude. In reality, they have large amplitude. And in other ways, on the xp and the tx plots, you can see triplication somewhat like this and this. So you can see that between B and C, there is retrograde motion. Between D and B, there is prograde motion. Between C and A, there is prograde motion again. So for the forward branches, dx by dp are less than 0. For the backward branch, dx by dp is greater than 0, and this is associated with prograde motion, this is associated with retrograde motion, and this is associated with prograde motion again. And on the tx plot, if you will see that three rays are coming at the same time, and this phenomena is known as triplication. And in terms of intercept and the ray parameter, then what you will see that on the forward branch associated with prograde motion, there is this blue color dot which can be seen at the prograde motion plot, where del square tau by del d delta square is greater than 0. This on the backward branch associated with the retrograde motion, the yellow color dot can be seen, or you can say can be traced at the retrograde branch, and that is basically related to del square tau by d delta square less than 0. And the red color dot can be traced at the prograde branch, that is d square tau by d delta square greater than 0. Now, mathematically, if we talk about the concentration of the rays, then the concentration of the rays are proportional to di by d delta, where I is the incident angle. So what we can say, the range of incident angle for the rays that arrive in a given distance. To find this, for the case that we are seeing here for the triplication, we differentiate the definition of ray parameter, that is P is equal to R sin I by V. In that case, if we are differentiating the ray parameter with respect to the distance, that means dp by d delta, that will be equal to del square d square t by d delta square. Then that will be d r sin I by v by d delta. And if you will differentiate it with respect to the distance, then what you will get r by v cos I di by d delta. So for triplication, the backward branch meets the two forward branches, as we have seen. At 2 points they meet on the travel time and the p delta curve. And for triplication, as we have seen at point B and C, dp by dx should be infinity, because those are the caustic points. Then this dp by da delta is equal to infinity. So large amplitudes are expected, and this situation is called caustic. Now talk about the velocity distribution case 3, that is the case of shadow zone, where the low velocities are found. So if suppose the earth is smoothly having the increment in the velocities with depth, and suddenly there is a low velocity layer, then in that case a shadow zone will arise, because the ray turns more vertically, creating a shadow zone. Let's suppose rays are basically going in the normal situation, but suddenly they experience this low velocity layer here. Then the rays will start to have the turns that are more vertical, and then they will create a shadow zone here. That means there in this zone, no rays are being observed. So for a ray to bottom, it must turn upward to a larger angle of incident as it goes deeper to a small value of r. So di by dr is less than 0. In low velocity layer, di by dr is greater than 0. The ray turns downward and cannot bottom. So in the real, or you can say in the normal earth situation where the velocities are smoothly increasing, the rays are basically turning away from the normal, having the larger value of the incident angle as it goes down. That means the di by dr will be less than 0, since as it goes down, the value of r is keep on decreasing. So in that case, di by dr should be less than 0. But in case of low velocity layer, because the rays are turning more vertically down, then di by dr will be greater than 0. And if you look at on the travel time curve for time and the distance, then you can see there is this shadow zone where no rays are being observed. And this is the plot for ray parameter versus distance. You can see again there is this shadow zone, and same thing for the intercept time and the ray parameter. And if we try to find out the condition for the occurrence of the shadow zone, then we can again consider the case of sin I, where sin I is equal to PV by R, and if we differentiate it with respect to R, then it can become cos I di by dr, and then P, since P is going to be constant, and then what you can observe 1 by r dv by dr minus v by r square. And then further, if we calculate the p from there, then that will become sin I 1 by v dv by dr minus 1 by r, and thus di by dr what you will observe is equal to tan I 1 by v dv by dr minus 1 by r. So if we take dv by dr out, then or if you will keep di by dr as I have explained in the previous slide, should be basically greater than 0. So it should be greater than 0. When you will apply this condition here, then what you will see dv by dr should be greater than v by r. So for the occurrence of the shadow zone, this condition must hold true, and this causes a shadow zone, a region of the Earth's surface where no rays will arrive. So this example has been taken from the book of Connect, and you can see the velocity model for S wave, and this is the velocity model for P wave. Then when we compute the travel time versus the distance curve, then what we can easily observe, there are the shadow zones over here associated with this low velocities. Now let's talk about travel time curve inversion, that is basically used to infer the velocity distribution with depth, and it requires sophisticated computing based on Snell's law in order to trace the rays within the different velocity layers and compute the corresponding travel time curves. And it is then used to derive velocity structure from the travel time curve. In this travel time curve inversion, we generally follow iterative techniques, and it basically solves the inverse problem, where the forward problem is solved repeatedly until a satisfactory solution is found. For this purpose, we take this integral into consideration, that is the Herglaus-Wiechert integral, and which says that delta p is equal to 2p integral from the bottoming depth to the epicentral depth dr by r in bracket zeta square minus p square to the power under root where zeta is equal to r by v, and p is the ray parameter for the ray arriving at delta, and this whole thing can be written as something like this, where the delta 1 defines the bottoming point of the ray, and zeta 1 is defining r1 by v1 at radius r1. r1 is the radius at which the ray is bottoming up. This formula we can use by starting with an observed travel time curve T delta and form a derivative, that is dt dt by d delta is equal to p delta numerically. The integral is done numerically from delta is equal to 0 to delta is equal to delta 1, using the fact that zeta 1 is equal to dt by d delta at a distance delta 1. The equation then will provide you the radius r1 at which the velocity is r1 by zeta 1. That means the depth at which the ray is bottoming up, and it will provide that velocity. One thing that we must note that this method fails when there is velocity decreasement in with depth, and or you can say it fails wherever the low velocity zone exists. If we concerned about the summary of today's lecture, then it goes like this. The travel time curve T delta is concave downward because its slope is P delta, that is ray parameter, that decreases with distance. That means dp by d delta is less than 0, or you can say dp by d delta, which is equal to d square t by d delta square, that will be less than 0. Rays that bottom in the region of high velocity gradient are bent upward more and emerge at a smaller value of delta than would otherwise be the case. The P delta and T delta curves have three distinct branches: two normal forward branches where dp by d delta is less than 0, and the back branch where the delta is decreasing and the p is also decreasing. Dp by d delta will be greater than 0. For triplication, the back branch meets the two forward branches at 2 points, that is basically caustic points on the travel time and the p delta curve, and for triplication to happen, dp by d delta should reach to infinity. Hergoulos-Wiechert integral is an approach that is used for travel time inversion, and that gives the distance traveled by a ray with ray parameter p as a function of velocity structure. The expression or the integral is basically something like this, that is delta p is equal to 2p integral from bottoming depth to the epicenter depth dr by r in bracket zeta square minus p square to the power under root. These are the references, and we will meet in the next lecture, that is the lecture 3 of module 6. Thank you so much. Bye bye.